about the quantum algo. How we use the algorithm in the quantum computation. So, in the quantum computing, a quantum algorithm is an algorithm that runs on the realistic model of the quantum computation. Most commonly used model being the quantum circuit model of the computation. Means when we are talking about a quantum computing, then we use the quantum algorithm. So, a classical, apart from this, a classical, which is the non-quantum algorithm, is a finite sequence of the instructions or step-by-step procedure for solving a problem, where each step or instructions can be performed on a classical computer. Similarly, in the quantum algorithm is a step-by-step procedure where each of the steps can be performed on the quantum computer. This is meant for the fast processing as well as for all the quantum equations can be solved by using this algorithm. So, although all classical algorithm can also be performed on a quantum computer, the term quantum algorithm is generally reserved for the algorithms that seems inherently quantum or use the some essential features of quantum computation, such as quantum superposition and quantum entanglement. These are the main features of the quantum computing: quantum superposition and the quantum entanglement. Keeping in mind these features, quantum algorithms are used, and they are used to perform on the quantum computation. So, what is the quantum algorithm? So, if we talk about the definition of the quantum algorithm, it is a step-by-step computational procedure that runs on a quantum computer and designed to take the advantages of quantum phenomena or the quantum features like superposition, entanglement and the interference. So, these features must be keep in mind whenever we use the quantum algorithm step by step. Now, unlike the classical algorithm that operates on the bit 0 and 1, now the quantum algorithm used on the qubits. So, qubits, quantum bits that we already defined. So, whenever we talk about the quantum algorithm that work with the qubits, that is the quantum bits that can exist in the combination of the states, and dramatically increasing computational flexibility and the speed of the speed to solve the problems. So, how do quantum algorithm work? So, again, as in the classical, we use step-by-step procedure. Similarly, here we use the step-by-step procedure. At its core, a quantum algorithm typically consists of the following step. Number 1, initialization. So, first prepare the qubit in a non-quantum state, often starting with all qubits in the 0 state. That is representation of the qubits. So, it is defined in terms of the cat and bra. So, this first step is the initialization. Second step is the quantum gate operation. So, apply a series of quantum gate such as Hadamard or the C0 and the phase shift gates to manipulate the state of the qubits. So, we just manipulate the state of the qubits by using the various procedure. Third step is the interference and the entanglement. So, use the entanglement to correlate qubits and interference to amplify the correct outcome while cancelling out the wrong ones. Here we define the interference and the entanglement step, where there is a correlation between the qubits, means as we have given the example already, then we use the entanglement. So there must be a correlation between the qubits that can be solved by the interference and entanglement steps, and so that the output which we are getting must be in a correct manner. So next is the fourth, which is the measurement. So fourth is the observe the quantum state, collapsing it into a classical output. Measurement means observe a quantum state, collapsing it into the classical output like 0 and 1. Means whenever we are having the states, just to close the window, so we use the quantum measurement as a collapse, as in the 0 and 1 output. In the quantum we also get the various output. So what are the difference between the quantum algorithm and classical algorithm? One of the key difference between the quantum and classical in how they explore the possibilities. Classical algorithm operate in the linear step by step position. In contrast, quantum algorithm can explore the multiple solutions simultaneously. That is a entanglement and that is a superposition, and because of superposition it can solve the multiple solutions simultaneously, but in the classical it is solved step by step. So in the quantum we just solve the problem. Moreover, we can solve the multiple problems, correlated problems easily in the quantum algorithm, and this parallelism allow certain quantum algorithms to offer exponential or quadratic speed up over the best known classical method. Whenever we require the parallel computation solving problem, so we require the exponential or the quadratic speed up over the best known already defined the classical method. So superposition and the keeping in the mind the superposition as well as the entanglement, we can define the quantum algorithm. For example, the two algorithm we always use, first is the Shor algorithm, second is the Grover algorithm. So example, which is the Shor versus the classical factoring. So take the Shor algorithm for factoring large number. So while classical computer struggle with this problem, a foundation of the modern encryption, so Shor algorithm can in the theory solve it efficiently, posing both a threat and a promise. Like another example is the Grover algorithm, that is versus the classical search. Means two algorithm we will use. First we factor, just we divide the problem into the smaller parts. So we use the Shor algorithm. Moreover, another is the Grover algorithm whenever we are doing the classical search. So Grover algorithm can search unstructured data sets quantically, so faster than any classical approach, showing the breadth of the quantum advantage across the domain. The Grover algorithm can search the unstructured data sets quantically, so it just give the faster and speedy result as compared to the classical. So in short, quantum algorithm are not just faster programs, they represent a paradigm shift in how we think about the computation, and the computation hardware steadily matures. The race to develop and implement the new quantum algorithm that will define the new revolution in the computing. So that as we are just making the quantum computer faster, so we require the algorithm so that it can work on that computation. So algorithm based upon the quantum Fourier transform, algorithm based upon the amplitude amplification, algorithm based on the quantum walk, BQP complete problems. So we use the algorithm that solve the complete problem so that it will be easy just to handle this. Another is a hybrid quantum classical algorithm, means the algorithm that work on the classical as well as on the quantum. So hybrid algorithm we also use. So algorithm based on the quantum Fourier transform, The quantum Fourier transform is the quantum analog of the discrete Fourier transform. Discrete Fourier transform means here we are having a various steps of the transformation, and it is used for the several quantum algorithm, and simultaneously it can solve, or the multiple solutions can be done through this Fourier transform in the discrete manner. Moreover, the Hadamard transform is also an example of the quantum Fourier transform over a n-dimensional vector space over the field. Over the field. So, n-dimensional vector space is used in the Fourier transformation. The quantum Fourier transformation can be efficiently implemented on the quantum computer using only a polynomial number of the quantum gates. Another is the Dutch-Zosa algorithm, that is used for the black box problem solution, and that requires exponentially many queries to the black box for any deterministic classical computer, but can be done with a single query by a quantum computer. Means there is not required a multiple query, the problem that requires exponentially many queries to black box, but we can give the single query and we can solve it in a very precise manner. However, when comparing the bounded error classical and quantum algorithm, there is no speed up, since a classical probabilistic algorithm can solve the problem with a constant number of query with the small probability of errors. So, algorithm determines whether a function f is either constant 0 or the balanced means we can have the two output, maybe constant or the balanced output. Constant output 0 on all inputs, 1 on all inputs, or balanced is the return 1 or half of the input domain and 0 for the other half. Means it returns 1 for the half and return 0 for other half, means it will be in a balanced manner, all the 0 and 1 will be written, but in the above, that is a constant, it will be 0 or it is written in the 1 full. So, this is a schematic explanation of the algorithm. Here we are 0 and 1. Now we can get the output in the desired form. So, another is another algorithm which is the Bristin, and that is explained by the first quantum algorithm that solve a problem more efficiently than the best known classical algorithm, and is designed for create the oracle separation between the BQP and BPP. Another is a Simon algorithm, that Simon solves a black box problem exponentially faster than any classical algorithm. So, including the bounded error probabilistic algorithm, this algorithm which achieves an exponential speed up over all the classical problems that we consider efficient, and was motivation of the Shor's algorithm for factoring. Another is the quantum phase estimation algorithm. So, the quantum phase estimation algorithm is used to determine the eigenphase of the eigenvector of a unitary gate. So, given the quantum state proportional to the eigenvector and access to the gate. So, the algorithm is frequently used as a subroutine in the other algorithm. So, quantum phase estimation algorithm used for the eigenvectors of the unitary gate. Another is a Shor algorithm. That algorithm solve the discrete logarithm problems and the integer factorization problems in the polynomial time, and whereas the best known classical algorithm take super polynomial time, it is known whether these problems are in the P or NP complete. So it is unknown whether this problem is P, NP complete. It is also one of the few quantum algorithms that solve a non-block box problems in polynomial time. So Shor algorithm which solve the non-black box problem in a polynomial time, where the best known classical algorithm run in the super polynomial time. So we can solve the problems which is in the non-block box, so by using the polynomial time. So next is a hidden subgroup problem. That is Evelyn hidden subgroup problems is generalization of many problems that can be solved by the quantum computing, like Simon problem and like Pell's equation, testing the principal idea of the ring and factoring. Means whenever we just solve the factoring problem, then we use the SOR or the subgroup, hidden subgroup problems. So there are the efficient quantum algorithm which is used to solve the hidden subgroup. Abelian algorithm are used to solve the hidden subgroup problem. The more general hidden subgroup problem, where the group is not necessarily abelian, is the generalization of the previously mentioned problem, as well as the graph isomorphism and certain lattice problem that can be solved by the hidden subgroup problems. Efficient quantum algorithm are known for this is the certain non-abelian groups. So however, no efficient algorithm are known for the symmetric group, which would give an efficient algorithm for the graph isomorphism and the dihedral groups. So, which will solve the certain lattice problems. Another is estimating the Gauss sums. So Gauss sums is a type of exponential sum that must be solved by the quantum algorithm. So the best known classical algorithm for estimating these sum takes exponential time. So since the discrete algorithm problem reduces to the Gauss sum estimation, an efficient classical algorithm for estimating Gauss sum would imply an efficient classical algorithm for computing the discrete logarithm, which is considered unlikely. So however, quantum computers can estimate Gauss sum to polynomial precision in the polynomial time. So Gauss sum estimation can be solved by using the quantum algorithm. Another is the Fourier fishing and the Fourier checking. So whenever we develop the quantum algorithm, so these are the some features which keep in mind to just use the quantum algorithm. So if we consider a oracle testing consisting of an n random boolean functions mapping n bit strings in the boolean value with the goal of finding n bit string from Z1 to Zn, such that the Hadoop mode Fourier transform can be have the value at least 3/4 of strings satisfying the particular equation and at least 1/4 satisfying. So this can be done in the bounded error quantum polynomial time. So algorithm on the amplitude amplification, that will be the Grover algorithm. So amplitude amplification is a technique that allows the amplification of the chosen substrate of a quantum state. Like amplification will be required so that we can give the desired result. So application of the amplitude amplification usually lead to the quadratic speed up over the corresponding classical algorithm in case of the searching. So it can be considered as a generalization of the Grover's algorithm. So what is this Grover's algorithm? Grover's algorithm searches an unstructured database where we don't have a structured database. So we use the Grover algorithm or an unordered list in which we can search the particular domain. So if we talk about the Grover's algorithm, it searches an unstructured database or an unordered list with the n entries for a marked entry using only O root power n queries instead of O n queries requires classically. Means we are searching through the Grover algorithm by using the O n queries in place of the O n, as is the queries O root n queries for the unstructured database. Right? No, classically O n queries are required even allowing the bounded error probabilistic algorithm. So theorists have considered a hypothetical generalization of a standard quantum computer that could access the histories of the hidden variable in the Bowman mechanics. So such a hypothetical computer could implement a search of an n-item database in at most O root 3 root power n steps. So such a computer is completely hypothetical and would not be standard quantum computer or even possible under the standard theory of the quantum mechanics. So this is slightly faster than the O root n steps taken by the Grover algorithms. However, neither search method would allow either model of the quantum computer to solve the NP complete problems in the polynomial time. So Grover algorithm can speed up the searching by sending a single query, and the search result we can efficiently in a faster and in a efficient manner. Another is a quantum counting. Quantum counting solves a generalization of a search problem, and it solves the problem of counting the number of marked entries in an unordered list. Counting means here we are having a marked entries of the data in a unordered, it is not a structured. What is it? Is not structured. So unordered list with a marked entries can be searched through the quantum counting instead of just deleting whether ones exist. So specifically, it counts the number of the marked entries in an n element list with an error of at most sigma by making only theta epsilon minus 1 root of n by k. So we can we can find out the error at most epsilon by making only the theta epsilon minus 1 root n by k queries, where the k is the number of the marked element in the list, n is the total number of the elements in the list, but k is the marked list. So more precisely, the algorithm output an estimating k for k the number of the marked entries with the accuracy of this k dash minus k less than equal to epsilon k. So these are the basic requirement of the quantum algorithm as well as which algorithm we can use. So now in the next lecture we will continue about the quantum algorithm. Thank you very much.